Okay. Yes. Dear colleagues, my name is Leonid Lyubchik. I am a professor of National Technical University Kharkov Polytechnical Institute, Department of Computer Mathematics and Data Analysis. In our department, we have a scientific team which work in the field of mathematical modeling and machine learning with application to large-scale system analysis and design, particularly in the field of application of this method to the dependability and reliability analysis. So we present two papers devoted exactly to the some topics from the mathematical models and other to the machine learning. The first our paper is safe valued Markov chain dependability model with uncertain data. The brief content, we will discuss the very important, very interesting problem of theoretical foundation of the analysis of reliability system, well-known methods. It is Markov chain model, but in last years, great attention was devoted to the development of these methods, to the situation of uncertain initial data. Then the parameters of the models is not exactly known, and we should apply some methods of uncertain analysis. For example, it's called set-valued Markov chain and another, and we will consider the new approach to interval estimation of Markov model. Exactly, it is a method which interval estimation via optimization approach. It gives us the possibility to obtain some results with lead to effective analysis with large scale model. And first of all, it is well known that the dependability analysis consists for construction, solution, and suitable models. There are a lot of models maybe applied to this problem. Most important from this it is maybe stochastic patterns and Markov chain model. Markov chain model is maybe most popular, most effective approach to the modeling of different situation is dependability reliability analysis. But in real problems, transition matters of dependability Markov models as a rule is not exactly known, since these matrices are estimated from the results of experiments. So when we find some approach which suitable to consideration of real system, it is necessary to take into account that the parameters of our model don't exactly known, and we should apply some methods of the asserted analysis. It may be interval analysis, maybe probability analysis, maybe another, but from the practical point of view, it is more suitable the called interval analysis, which based on the set value description of the uncertainty of such objects. We will consider this problem and uh, effective methods for self-valued Markov chains analysis and set description of uncertainties uh, give us the possibility to find the bound characteristic of transcendent steady state probabilities of Markov process, and interval analysis approach is also may be extended to most complicated situation. It may be in homogeneous Markov chain with variant parameters. Interval Markov chain that provide us to obtain the upper and lower bounds of probabilities, and this cover all possible scenarios for evolution of state probabilities. One of the most important main interesting problem associated with the application of interval analysis methods to uncertain Markov chains, this connected with the computational complexity, because interval mathematics from the computational point of view, it is a very difficult mathematical approach, because it is connected with some transformation of geometrics objects, of multidimensional geometric objects. It's connected with a different complicated methods of the calculation of such estimates. So the main idea of our work is to obtain the most effective methods which connected with another idea of the obtained of lower upper bounds of probabilities which are the consideration. It is optimization approach. We proposed a new approach to interval estimation for Markov models with uncertain parameters, which based on optimization technique to obtain boundary estimates of both transition and station probabilities. Main idea of our approach, it is a transition from the description of uncertain transition matrices using a set of polyhedral multidimensional space to the description using a family of approximated ellipsoids. Using ellipsoids and the description of a certain structure of initial data give us the possibility to obtain very effective computational procedure which gives us the estimates of probabilities of the state of the system as a result of not very difficult solution from the spatial optimization with linear functional and quadratic constraints. The developed techniques made it possible to significantly simplify the numerical procedure of upper and lower bounds estimate of transitions and steady-state probabilities and unify consideration of various uncertainty models. So, main results of our work, it is from our point of view, it's some general technique of self-valid Markov chain models analysis based on ellipsoid approximation. We solved two problems. First, it is interval estimate of steady-state probability vector of continuous time Markov change, and another problem, it is interval estimate of transient state probability of embedded Markov chain in discrete time. Some theoretical background is well known. It is a typical description of Markov models, which consists from the transition behavior Kolmogorov differential equations. It is well known that the steady state probabilities may be found as a solution on linear equations. It is equation with connected with the generated matrix of continuous time Markov change, but in our situation, we consider the problem of find of solution of this equation from the steady state probability, taking into account the special restriction to the unknown genetic matrix. For example, it may be restriction as a linear inequalities for all elements of this matrix. It is not very difficult to obtain the upper and lower bounds of all elements of the generated matrix from the initial data, for example, for file race and another characteristics of real problem. And using this description, we consider another problem. It is a problem of set valued embedded discrete time Markov chain. It is the typical model which describe this situation, but we added the uncertainty set which describes the uncertainty in the transition matrix elements. So about the problems. It is first problem. It is the interval estimate of steady state probability vector of set value Markov change. It is necessary to find an interval estimate using the so-called polyhedron descriptions of the uncertain parameters, and we will find these characteristics of uncertainty as the maximum minimum components of normalized solution on literal linear algorithmic equations. And another problem, it is interval estimate of transition state probability vector. Such the problem connected with obtain the recurrent equations, which give us the possibility to step by step calculate the constraints and the upper bounds of the probability vectors using the well-known dynamic equation of matrix chain. Some words about the solution on this problem. First problem, we find the characteristics of uncertain uh, set which describe the solution of steady state Markov model or steady state solution Markov model as an optimization problem. Find the optimization of linear functional, this additional constraints which describe our uncertain characteristics. But from mathematical point of view, it is one problem. It is linear optimization problem, linear programming. But in the situation where they have high dimension, the solution of this problem, of course, very difficult. But it is there are another difficulties. The solution of linear programming problem is very sensitive to changing of initial data. And in another situation, it is necessary to obtain the solution that have some characteristics with low sensitivity, because it is necessary to take into account that all of our initial data has errors. It is as a result, we propose the transition from the linear programming problem to the linear quadratic programming problem using the ellipsoid approximation of the characteristics of our uncertainty. In such a case, using standard methods of the solution optimization problem, we use Lagrange function approach. It is very easy to obtain, in fact, analytical solution of this problem is described in this slide, but Lagrange multipliers will be found as a solution of nonlinear algebraic equations, and the result we obtain the estimation with the help of very simple computational procedure. Another steps, it is obtained the characteristics of transient behavior or probability interval vectors, and in such a case, we using the ellipsoid approximation, we give the step-by-step algorithms, we give us the possibility to obtain ellipsoid approximation as a recurrent equations in the probability state space. A solution was obtained using constraint optimization Lagrange function 2, and this describe the results as a recurrent procedure to obtain this characteristics. And a little example is very simple, but it demonstrates the possibility to apply this approach to the real problem. Of course, in the field of large dimensions, computational methods with such proposed approach, but in this simple simple example, it is very easy to see the effective results of this approach. We consider the model taken with these papers. It is a benchmark model with very fast use in order to illustrate some methods. It is very simple object, only 4 states. Uh, these characteristics of uh, these characteristics of these states of our system transition describes the transition from one state to another. Some parameters were taken of the paper which I mentioned here, and the results. Using our approach, this is a model transition graph and generated matrix which used in order to illustrate the computational method, and sorry, and these results of computations. It is a system probability, the probability to state 1 normal function with connected with the parameters of our system, and this is a demonstrates the possibility to apply our upper and lower bound of probabilities. We consider the for the is a computation, we consider situation that the uncertainty is equal for all elements of transition matrix, but in the general situation, it very easy to obtain such the diagrams for any type of uncertain characteristics of our system. And thank you for your attention. Thank you. Your question, please.
Okay, thank you very much for your presentation. And now we have time for questions. I have one question, if it's possible.
So of course. Of course.
6 months ago, we tried to use interval mathematics for Markov based Markov model based analysis, but we got some problems related to logical interpretation of result, assessment of final probability of states regarding to intervals of initial parameters, similar failure rate, failure recovery rates, and so on. You suggested a method of optimization, and my question is two questions. First one, what about the guarantee of logistic corresponding changing of initial parameters and final probabilities? And second one, if you can say about what is the difference between optimal and non-optimal rational decision according to your methods. Thank you.
No, thank you. First question about the dependence. Of course, when we use any methods of taking into account uncertainty in the describing of the solution of Markov model, it is necessary to investigate the dependence between the uncertainty of initial data and the final the results of the steady state, for example, probabilities. But of course, it may be done only by numerical experiments, because, of course, it is not possible to obtain the analytical dependence from the characteristics of uncertain probabilities and uncertain parameters. Of course, any approaches, any methods, from my point of view, which may be used in such a field, must take into account the possibility of analysis of sensitivity of the results from the initial data. And the second question
concerning optimization.
Optimization. Да. What about optimization? In our approach, optimization, it is only the instrument to obtain the solutions, because when we use interval mathematics as the basic instrument to obtain the results, it connected the some geometrical transformation in multidimensional field space. It is from the computational point of view very difficult, but not only from the computational. The assessment of the dependence in such a way is very difficult. And when they use optimization approach, we give the very simple path of obtain the solutions. And another, of course, verification, validation, this model, another take us the possibility of analysis of sensitivity and dependence in such a way too. Thank you.
Thank you. Any other questions, colleagues? I don't see any questions. Okay, Hans, thank you very much.
Thank you again.
Thank you. Thank you.